All right, let's do another example for optimization. So we've got a bit of a different situation here. In the last problem we were looking at, we were trying to maximize volume, and now we're going to do a problem that's more about efficiency. We're trying to minimize the amount of time it takes, in this case, for a dog to run down a beach, jump in the water, swim through the water to a ball to retrieve the ball, right? So let's go through kind of just the setup here. I've already got a picture drawn to show what's going on. And we want to go through those steps of having, like, what are we trying to maximize or minimize? What are our constraints? What are the constraint equations? Can we substitute things in to determine a function that we can optimize, that we can get its maximum or minimum values for, etc. Right? So that's the big picture, what we're trying to do here. The specific problem is that we are setting up this fun scenario, and this is a classic. This is like, you'll see this problem in like every calculus book that you ever come across. It's just a very traditional setup problem to introduce students to the idea of optimization. So you're standing at a coastline and you throw a ball into the water, right? So we're right here and we throw the ball and it lands right there. And this is water here, but we have sand on the bottom side of the water line here. So the ball lands 100 feet down the coastline and 60 feet perpendicular to the coast in the water, right? So we start by just having these distances so we can see where the ball is compared to where we threw it from. I've got a dog, and my dog runs down the coast a ways and then jumps into the water and swims at an angle out to the ball. So the dog doesn't run, let me change my color, make this a little easier. The dog doesn't run all the way down to here and then go at 90 degrees to the ball. That's not what dogs tend to do. And they also don't jump immediately into the water to go for the ball. You can actually do experiments with this, and they come up like just naturally with a pretty good answer that's close to what we're actually going to calculate as the mathematically optimal location to jump in. They run partway down, and then they jump in the water, and then they swim out to the ball. So they're trying to get as much distance out of the way while running on the sand, because they can run faster than they can swim, but they're not going to run all the way to a 90-degree angle. They're going to kind of just intuitively kind of say, this is a good spot to jump in and overall get to the ball the fastest. So, and we're going to assume that the dog can run 25 feet per second and in the sand and can swim 10 feet per second. So those are some important values here. So we want to find the optimal location, but what are we trying to maximize or minimize? We are trying to minimize the time to the ball. So we need a function for time. Okay, so we're going to break this up as time running plus the time swimming. Now we'll get expressions for those here in just a minute. Now, what are we constrained by? Well, we have the run speed of 25 feet per second. We have the swimming speed of 10 feet per second. So those are some key things, but we also have the distances. We have the 100 feet down and the 60 feet into the water perpendicularly. And so how do we want to manage those distances? Well, what we really need to be thinking about, we can just list them. The 100 feet and 60 feet are also constraints, but how are we going to work with these for the time? So let's think about, what is the time running going to equal? We want to use the fun little formula. Distance equals rate times time, our classic physics formula here. And so we can reorganize this as time equals distance over rate. So the time running is going to be the distance running over the speed running, and that's 25 feet per second, right? And the time swimming is going to be the distance swimming over the speed that our dog can swim here, which is 10 feet per second. And so what we need to figure out is the distance that the dog is running and the distance that the dog is swimming from our picture here. And this is also something that's mentioned as we look through the way that the problem is worded. So it asks for the optimal location. Where does the dog jump into the water? So let's give that a variable. Okay, so let's let x be the distance the dog runs before jumping into the water. So our time running is going to be x over 25, and we'll plug that in just to kind of get it out of the way here. But then our swimming distance is here. Let's call this y. I could say y over 10, but we don't want to have two different variables. We want to see how do x and y relate. And this is where the picture really comes in handy, because we can see right here this handy little right triangle. And one of our favorite little formulas that we see in a lot of geometry problems that help us relate different things when we see right triangles is our Pythagorean theorem. So I'm going to start by recognizing that this distance that I'm drawing right now in green is 100 minus x. And that's really key that we recognize that distance in terms of x, because then we can say that 100 minus x squared plus 60 squared is going to equal the y squared. So we can say that y equals the square root of all of this, and I'm actually gonna, I'll pull this up. I'll show you how I want to simplify this, because I'm going to use a computer whenever possible to work through some of this math. So I'm going to take this and, 1 second to pull this up. Okay, so I just pulled up GeoGebra real quick, and I just, I've got this formulation, but I just want to expand that inside. So that's x squared minus 200x plus 13,600. So let me go back here and I'm just going to rewrite it. X squared minus 200x plus 13,600. Come on. So we can put this in for our function t, and then we have t as a function of x. I'm going to write this as 1 over 25 times x plus 1/10 times, and I want to use exponential notation rather than root notation because I'm going to take a derivative. But before we do that, let's just think about the domain of our function. Okay, because we want to think about like what's the smallest x value and biggest x value that might make any sense. And I think the dog jumping into the water immediately, not running at all, so x is 0, would be kind of the smallest nonsensical number to put in here. And then the biggest would be 100. The dog's not going to run past where the ball is and then go backwards. So we know that our our minimum time is going to occur when x falls somewhere between 0 and 100. And then we want to find what is t prime. And again, like we can do this by hand, but I'm going to do it on GeoGebra real quick, see if it can't just kind of do some of the work and simplification for me, because this is a fun chain rule. I'm also going to do most of my solving in GeoGebra, so let's take a look at how that's going to come together. All right, so I've got our function t of x in here, and I'm just going to do t prime of x. And that is ugly, so I'm going to copy that over to the page in a second. We might actually be able to get a little bit prettier form if we were doing that by hand, but what we really care about is the critical numbers, right? So we want to solve 0 equals t prime of x, and look at that, it's spitting that out right away for us. And we can do that as an approximate number right there. Okay, so let me just, you can rewind, I'll slow that down one more time. Oh, here we go. So I just typed out solve 0 equals t prime of x, and it spit out that number for me. So let's see if I can't just get this on my screen with the annotation software. 1 second. All right, so I've got my stuff over here from GeoGebra that I can see, and let's just go ahead and copy some of this stuff down. T prime of x equals 1 over 50 times 5x plus 2 root. There's our fun x squared minus 200x plus 13. 600 expression that is causing us so much grief here, just making everything super tedious to get through. But we're just going to follow the steps and let the computer do a lot of the work for us. Okay, and when we set 0 equal to t prime of x, this gives x equals negative 40 square root of 21 plus 700 over 7, which is approximately 73.8 is just fine, just a single decimal place. And so we can check the end points as well. We're going to check, so this is our critical. Check endpoints of domain and criticals. So we want to do t of 0, t of 73.8. Let's put that in as the exact value here. So negative 40 square root of 21 plus 700. I just want to avoid rounding error. So we'll put that in exactly. And we'll use our rounded number for our conclusion still. And then t of 100. And again, let's not belabor this. Let's go ahead and just say keyboard. Close this out of the way. T of 0, t of 100. Those are the easy ones to check. And then we want t of negative 40 square root of 21 plus 700 over 7. Cool, and so we get a smallest time out of the 3 is 9.5, and that was in feet per second, so that's 9.5 seconds to get to the ball there. Let's go ahead and copy this down. Zero is 11.7 seconds. T of the 73.8 is 10 seconds. And the T of 100 is about 9.5 seconds. So let's just read the problem, make sure that we're answering everything. I assume the dog could run 25 feet per second in the sand and could swim 10 feet per second. What did I find the optimal location to be? So it just wants to know about where the dog is jumping into the water. And we're seeing that that happens. Oh, I just flip-flopped these answers, didn't I? My apologies. Let's see if I can So the minimum time to get to the ball is about 9.5 seconds. And while we didn't have to report that, it's still a nice thing to put in our conclusion. Like if you were actually doing some sort of analysis for your job, you would not mention that, right? So we're just going to go ahead and put it in there just to be complete and thorough in our conclusion. And this happens when the dog jumps into the water about, let's say, after running about 73.8 feet. Cool, and that's it, and that is this problem. So I'm going to go ahead and sign off here. And again, I recommend comparing this to the steps down here. See that everything is lining up, and how I'm just kind of generalizing these steps in my head is just like this process that I'm following without having to memorize these steps explicitly. Is more just kind of like a internalized process for how I'm doing that. So that's it. If you want to pause and stare at this for a little while, go for it. But I'm going to go close this down, and I will see you on the next problem.